Good evening. We're in lovely Edgewood, New Mexico, at the home and laboratory of mad scientist Tom Caudell. Tom is a longtime mentor of mine during my days at Boeing and a good old friend. Uh, I'm Don Wunsch with Missouri University of Science and Technology, and today is February 27th, 2012, and we're interviewing Tom in his office, his home office in Edgewood.
So I'm Tom Caudell, and my official contact information is at the Department of Electrical and Computer Engineering at the University of New Mexico, and you can find me there. What else am I supposed to say?
Your
Formal education. My PhD and master's degree is in physics, particularly in astrophysics, and let's see, let me just look at it.
That was at Arizona, right?
University of Arizona in the physics department. Um, my first job was actually at Hughes Research Labs in Malibu, California, where I left the field of astrophysics and started working at their artificial intelligence center in the Malibu area.
Which is why we stole you.
No, that's not the reason. And
that's why we wanted to steal you.
and my interest in actual computational intelligence, it wasn't called that at that time, it was called neural networks, was when we were at the research labs, the Malibu Research Labs was supporting some people at the University of San Diego, UCSD. And we did an excursion down there probably in 80, gosh, it would have been 85 or 86, 1985, 1986, and I saw papers by Rommel Halt and people were, McClellan and people like that, people really, the pioneers of the field of neural networks, and fell in love with it instantly. We were doing rule-based stuff at the time, and I came back and started Hughes's first neural network project, IR&D project. And that's, by the way, why I got interested in virtual reality. Because as soon as I started doing neural network research, particularly in the area of simulation, I determined that we can't understand this stuff unless we could see the data in some way. And so just about that time, that was about 1987, an article came out in Scientific American, which I have around here somewhere, anyway, that showed the first virtual reality systems. And so it seemed to me that the best way to study neural networks and to visualize them was to actually immerse yourself in them. So I started Hughes's first VR project too.
Wow.
And that's been kind of my interest in VR all along. Was not my primary area of research, but as a tool for studying neural networks. So the first paper I published on it was in one of the IJC. It wasn't IJCN. It was
ICNN.
ICNN. It was in San Diego.
87.
Probably 87. Yes. And it was on parametric connectivity. It was this notion, because Hughes Research Lab was very interested in hardware, particularly optical computing. And coming from astrophysics, I was very interested in optics, and you did your dissertation in that topic area. So I was very interested in optical implementations, and so there was some technology being developed at that time that with some active light gratings and that sort of thing. And so I tried to figure out a way how you could use them for learning in neural networks. And the best way to do that was with genetic algorithms. And so I developed a system where we learned the emission patterns of a grating that would best map into the weights needed for a single perceptron sort of thing, and design that. And that was my very first paper. And I guess there were several more, and then of course at Boeing when we were together at that. The title was Parametric Connectivity, something about genetic algorithms. I forget the exact title. It was, like I said, so it was published in probably the ICN in 2007.
87.
87.
The very first one was in 87.
Yeah, I think so. Okay, want to just keep going?
Yeah, let's just keep going.
Okay, all right. So what persuaded you to study engineering and science? Actually, my dad was a ham radio operator, and when I was a kid, this tall, he was building transmitters and receivers of his own and that sort of thing. Wow. And I was looking over his shoulder and got interested in the smell of solder and all that sort of thing, and was determined I was going to be an engineer and build those sort of things. But then in high school, one of the first classes in my high school in Kansas City, Missouri at that time was we were allowed to go over to a central location and do some computer programming. And so I fell in love with computers and I wanted to build my own computer. And so I decided that the best place to build computers was in electrical engineering, and I was going to be an electrical engineer.
Okay.
And I started doing that, uh, and all the way up through high school. I was going to be electrical engineering. Even applied to Rolla at the time, but we moved to California, so I decided to do the junior college route because before going into the full, you know, big 4-year university sort of thing. And the second semester was there. I took a physics class and fell in love with physics and dropped electrical engineering
Wow.
and stayed in physics all the way through the end. But as soon as I got out and got a job, I was back into AI and computing and that sort of thing. So that's kind of my history on that sort of thing.
Oh, that's great.
I mentioned why I was really, really turned on by this notion of computational intelligence was because of the UCSD group. Their work was just amazing. The PDP books were out at that time.
Mm-hmm.
I fell in love with it so much that I actually taught 3/4 of I taught over a period of 3/4 a course in uh, neural networks, introduction to neural networks at the UCLA Extension
Mm-hmm.
on campus at UCLA, and just fell in love with it because it just was a beautiful blend of computing, um, sort of artificial intelligence, and engineering. And the whole, I'm an experimental physicist, and so the whole notion of being able to build these systems and study them and experiment on them was something that just really fascinated me. Um, so my first activity was to attend these ICNNs and the INNS meetings. I attended
Mm-hmm.
the first one of those in Boston as well.
Yeah, that would have been in '88.
88, yes, exactly.
Yeah.
Yeah, that was really,
That's
really
about the
fascinating.
time you came to us at Boeing, right? Right around then.
89, it was right
Okay.
after that. Yeah, I joined Boeing in 89.
In the nick of time.
Yeah. Um,
In the nick of
so,
time for Boeing.
what gives you the greatest satisfaction? What contribution gives you the greatest? My own contribution? Is that what you're like? Is that what this is?
Yeah.
Okay.
So.
Um, well, I don't think there is any greatest one. Just being able to be, we academics live a blessed life
We sure do.
of being able to spend the time studying the things we want to study, and to be able to have spent the last 35, 40 years studying neural systems has been the greatest thing I've really loved about it all. So
Well, I can
that's my
understand why
satisfaction.
it's hard to choose one. I love to tell people, I love to get it on video. You've got the Midas touch. Everything you touch turns to gold. So
Yeah.
you've done great work in the field. So.
Well, thank you very much. But I think in my industrial period, the thing I had the greatest satisfaction was at Boeing, the neural information retrieval system that we developed as a team
Mm-hmm.
and implemented, and actually was used uh, to do design retrievals from databases of existing designs to help engineers not essentially duplicate their efforts in some way. And the savings was going to be a huge amount. And we carried that forward with the help of our team even after I left. And in fact, I think at that time, if you counted neurons, it was the largest artificial neural network in the universe.
Yeah, it was the
Yeah.
artist.
It
Its
was
record may still stand. It certainly was a big one
it was a
because it was
gigantic one.
volume, so
Yes.
it involved a lot of voxels.
Huge,
So.
huge amount of information was stored in that. Anyway, so that was the satisfaction of actually starting out with these kind of architectures as a team, neural networks based on a lot on they were all adaptive resonance at the time, art ones, and seeing that through to something that was made into a computational tool and implemented and actually driven and pulled out to the divisions by people in the divisions, which was
Yep.
pretty amazing. That was quite satisfying
Yes.
to see someone do that because um, it, most of the time in industry, people don't care about this high technology stuff, right? And
Right. Well,
so,
a lot of research. It's research. It doesn't always see the light of day, but that one certainly did.
so the next question is what do I think the impact of neural networks has made on me? Well, it's launched me into my love of research. I mean, the impact is amazing. I just it has gotten it's actually drawn me into biology and studying biological systems and learning a huge amount about the brain. Nothing compared to what neuroscientists know, but I just trying to understand what's going on in the brain from a computational engineering perspective, and something we can build and something we can distill out and build into simple artificial systems. And that, to me, is something I think that has made a gigantic impact on me. The fact that we can do that, we can actually see, some of these very complex cognitive systems can be distilled down into relatively simple neural principles and then implemented on artificial systems and tested and experimented on. And to me, that's just had a major impact on me. And in fact, it's helped me get, you know, secondary appointments in the psychology department and things like that. So
Great.
it's really been very, very helpful. What impact have I made on the community? I have no idea.
Well,
It's never been something I don't have any kind of measure of that. It's just,
well, certainly the people you've worked with.
the people I've worked with have been, well, um,
You worked with me. You were
yeah,
like having a second advisor. You worked with Karen Haynes.
yes.
How
Well,
did that
yes,
impact
okay,
you?
so there's been a number of students I've worked with, and you, of course, that have gone out and been successful, in your case, very successful. So that's been probably an impact. But I just keep thinking that our impact that we'll make is still in the future.
Of course,
It's going to be, that's going to be where the impact is. It's not going to. We're always working up to it.
yeah, we're like being physicists that have the privilege of working at the time, combining Newton and Einstein being around and kicking, and
Hmm.
we get to rub elbows with people who are making real foundational
Oh,
contributions. So,
absolutely. In terms of the society, I think that the society has made a major impact on it. It legitimatized the field of neural networks by bringing it into an engineering society. And
mhm.
so I think that has been, phenomenal, because it was just kind of floating out there as a field, in AI circles and that sort of thing. So it really made it into an engineering discipline.
You remember at Boeing, we used to have to defend working on neural nets, and now you go there in some big project and they say, "Who's your neural net person?"
Yeah,
That's
exactly.
just music to my ears,
Yeah, exactly. Yeah, yeah, yeah. So I think that the IEEE and the INS both have made a big impact on that. And even so, even in the International Joint Conference on AI, IJCAI, they still
See
do a
neural
lot
net papers all the
all
time.
over the place. Right, exactly. And so it's funny that NIPS has been less neural networky. So anyway, neural information processing has been less neural networky. Anyway, so I think that has helped a lot, and getting the journal out and in society, I think is sort of formalized that legitimacy to people. But of course, with that kind of administration goes, you know, now you start having politics and
Of course.
competition and things like that, and that's a downside of any kind of society.
Right.
Is running it that way. But from a person in the trenches, that kind of stuff doesn't really affect us in any way. So hopefully. Um, how do I envision the evolution of computational intelligence technologies? Well, I think many of you know that about the nanotechnologies that are being used for implementing brain structures, the synapse programs that DARPA has, and other ones. And to me, I think that the, the there's a lot of theory we're developing, and people are developing in applications that deal with neural networks, and they're simplified, as I said, they're abstracted or simplified computation they're doing. But real brains work with those, but on a massive scale of hardware too. And
Hmm.
our simulations can never touch that right now. We can't
Right.
get anywhere near that. And there are things that you can do with these simple architectures that that you can't demonstrate these beautiful properties on small systems.
Do
They
you want
just
me to pause?
no, that's
Okay.
fine. And so, what I'm excited about is that a lot of these architectures and ideas that people are coming up with can actually now be on these neuromorphic hardware systems be implemented at a scale large enough that we can start seeing phenomena that will not appear in the smaller systems. And there's many biological phenomena that you see in biological neural systems that you would never see on a small system that happen just naturally on large systems.
Sure.
And so, and these are not weird exotic dynamical system things. They're just the law of large numbers sort of things. So um, anyway, so to me, that's where I think the excitement is, and it's happening now. And at the various conferences we've been at, they've talked about liter-sized 10 to the 13 neuron systems. And to me, having those and being able to program and do my experimental science with those as entities, simulating them and studying what they do is going to be phenomenal. But there's two other things I want to mention that I think are almost equally important that I'm beginning to see evidence of, and people are talking about it, but I think it really needs to have more focus, and that is in the sense of embodiment of computing, neural computing, that these cubic liter sized brains are sitting there, essentially a brain in a vat. It's like the young Frankenstein, sort of thing, right?
Yeah.
Abby normal, right? So these brains didn't evolve, neural systems didn't evolve in a vat. They evolved along with the bodies of animals in environments to do things, to survive, to help in lots of ways, right? They're part of the survival, Darwinian evolutionary process. And we as engineers tend to just put, training samples in, have a training set and a testing set, and we do all this sort of thing, and characterize their performance that way. But if we really want robots in the world moving around doing autonomous things and that sort of thing, they're going to have to be studied in bodies,
Yeah.
and in bodies in worlds. Now you can't do that effectively with hardware, because if I had one liter-sized brain, I'd have to put it in a robot and study it, and if I wanted to do multiple ones, which is the third thing I want to mention, you'd have to replicate them, and studies would be really hard to do. So to me, there's a real need to study the sense of embodying these brains in simulated agents that live in rich sensory worlds and have sensory and actuator apparatus. And that's something that we have been trying to study on a very small scale and working on, developing software tools for. But to me, that's where you start. And now you become a psychologist. You study this thing, or a neuroscientist. Design this brain. You put it in these bodies. You put it in a world, and you conduct experiments on it as a system, as an autonomous system, and study it and apply the kind of design of experiment that you do for biological studies.
And that's why you expect your visualization tools to help.
And that would help. The visualization would be essential in that case, because you want to observe this animal, but you can't. It's numbers in a machine. So the beauty of that, of course, is that we don't need to have imaging technology for these. We can digitally sample and study the brains in real time, doing whatever they're doing, and simultaneously watching their behavior. And to me, that's the second big thing I hope to and expect to see, that maybe these liter-sized machines could actually be used to simulate more than, or part of a regular von Neumann architecture that could simulate agents with bodies and sensors in worlds, along as well as their brains. So to me, that's an essential step for really progressing, because we just go far afield of testing these things when we use a training and testing set. Measure generalization and say that's a great architecture, right? But that may or may not be. It may be more than you need or less than you need in a biological system. What's the simplest thing you can get by? And I keep referring to, it's not here, but Valentino Breitenberg's book Vehicles. I recommend all my students read that book to get the sense of simple architectures doing complex things in bodies. So, and then the third thing is then to be able to use, I think is where we can go with this, is in the idea of social modeling. I think once we get these embodied neural agents with reasonable neural processing, then we can put thousands of them or tens of thousands of them in social structures and study them from that, from the simple swarming of bacteria all the way up to, flocking birds. And I don't mean just studying the mechanics of it, but the social structures that form.
Yeah, some of Patrick Grimm's Prisoner's Dilemma work is sort of like that. The Prisoner's Dilemma is an area where there's a lot more that can be done in that area, and there's some other folks that have.
Yeah, and that's a very small example.
Yeah, that's a tiny example.
Yeah, and so we've been doing some work in where does virtual crime come about? We've got some architectures that have crime because you put the amygdala in the system. Interesting things like that, right? How do you do that? Well, anyway, so so to me that's the third step, is that we really I see us going. Well, I don't know if I see us going there, but I think we should be headed that way and studying those forms of social interactions with these kind of embodied systems, because obviously you can't study social systems without embodiment, right? You can do it theoretically, but in terms of what they do and how do they learn these things, how do they get imbued with all this knowledge? They have to learn it through nurturing periods with parents and family. I mean, you have to have virtual families, and my point is that it's deep, hard work that I think that the computational intelligence people could really contribute an awful lot to.
Although autonomous agents on the web, they kind of have their own analog of a body, but that opens up a whole different can of
That's a
worms.
different
So,
thing.
yeah,
I'm talking about trying to understand real brains,
yeah.
real intelligence,
Hmm.
and it is not in a vat. So
Right.
anyway, so those are so it's breakthroughs in those areas that I think are going to be the most exciting things coming up, and the hardware that's being developed now, both the large scale parallel multi-core processors are helping with that,
Sure.
but they're not going to get where we want to go.
Right.
And to be able to study brains, simulated brains in virtual bodies at scale, doesn't have to be 10 to the 13 synapses, but it certainly be nice to be 10 to the 10,
Hmm.
and run in fast enough time so you can conduct large scale multi parameter searches of things, right? I mean, so you can't do that in real biological systems or with robots easily, right?
Hmm.
You can simulate, I want to run 1,000 different neural systems with each with 10, 10 to the 10th neurons in them over a period of effective time of months or years of their time in their world,
Yeah.
and do a statistical study of their behavior.
Hmm.
Well, welcome to the world of non-computational tractability.
Yeah.
So to do that, I think these synapse-like stuff, synapse isn't it's a DARPA project,
Yeah.
um, are the ones that will help us get there. And so anyway, that's my vision of someday being able to log on to these kind of neural computers and run these really large simulations and study them with our biological, psychological neuroscience colleagues and that sort of thing.
Yeah. We all can be customers of that.
Amen. Okay, I think that's
Great.
my final comments.
Well, thank you, Tom.
My pleasure.
Now